Here's a second law of thermodynamics problem, which tries to look at the efficiency of a Carnot cycle, but without actually looking at the temperatures directly. So if you're doing any thermodynamics, which you might be if you're doing engineering, and if you're a first-year student, or some people might even do this in high school, you will probably know that the efficiency of a Carnot cycle is given by 1 minus the temperature of the cold source over the temperature of the hot source or the hot reservoir, or however you want to call it. So you should know that the Carnot cycle operates between two temperatures, and two of the processes are isothermal processes. So you have this temperature being the hot temperature and this one being the cold temperature. So part A of the question is saying that find the efficiency if the gas volume increases by a factor of n, which in this case n is equal to 2. And then for part B, what is the efficiency if the pressure decreases by an amount n, where again in this case n is equal to 2. And we also know that the working gas is hydrogen, so we'll see what importance this has in a bit. So let's start with part A. So the question says that the volume increases during the adiabatic expansion or the isentropic expansion by a factor of 2. So the first thing we should do is to figure out where is the adiabatic expansion, and if you're familiar with the Carnot cycle, you should realize that it's between 2 and 3. So in other words, part A says that V3 over V2 is equal to N, which is equal to 2 in this case. Now, the efficiency of a Carnot cycle is not given to us in terms of volume, it's given to us in terms of temperatures. So let's actually rewrite this as 1 minus. So T cold would be this temperature here, which is the temperature at 3 and the temperature at 4, because they're equal to each other. So instead of Tc, I'm going to write T3. And instead of Th, I'm going to write T2. So the only thing left to do now is to express this T3 over T2 in terms of this volume ratio V3 over V2. And we can actually do that using the isentropic relationship between temperature and volume. But let's try to derive it and to better understand where that comes from. So we know that for an isentropic process, PV to the gamma is constant, right? And we also have the ideal gas law, which is PV is equal to mRT. So if we want something with temperature and volume, we should eliminate pressure, right? And that's why we use the ideal gas law. So we have pressure as the subject, which is mRT over V. Okay, so that is mRT over V, and then times V to the gamma is constant. So M and R are also constant, so we can actually put those on the other side and combine everything into just one constant. So this is going to be T over V times V to the gamma is constant. Or we can say that temperature times volume to the gamma minus 1 is constant. Because V to the gamma over V is V to the gamma minus 1. So let's apply that for the isentropic process from 2 to 3. So that gives us that T2 V2 to the gamma minus 1 is equal to T3 V3 to the gamma minus 1, which means that the ratio that we care about, the T3 over T2, is going to equal, so T3 over T2 is V2 to the gamma minus 1 over V3 to the gamma minus 1, which is V2 over V3 to the gamma minus 1. And that's it. So this ratio that we were trying to get with the temperatures T3 and T2 is also equal to the ratio between V2 and V3 to the power gamma minus 1. And the problem tells us that it's an isentropic expansion or an adiabatic expansion. So V3 over V2 is equal to N, which means that V2 over V3, because it's V2 over V3 that we have here, is 1 over n. So T3 over T2 will be equal to 1 over n to the power gamma minus 1. So the only thing left to do technically is just to find what the gamma is for hydrogen. So hydrogen is a diatomic gas, right? It's H2, which means that the gamma is equal to, so the gamma is always equal to the number of degrees of freedom plus 2 over the number of degrees of freedom, which for a diatomic gas, that's 5. So we've got this, and that's equal to 1.4, which is the same as for air. So T3 over T2 is going to equal 1 over 2 to the power 0.4. So that's 0.5 to the power 0.4, which is 0.758 approximately. So the efficiency is 1 minus this. So we're going to get a value of efficiency for this of about 24.2%, roughly. Okay, but this is just part A of the question. So in part A, we know that the volume increased by an amount of n equals 2. Okay, so part B says that during this adiabatic expansion, we don't know what happens to the volume, but we know that the pressure decreases by an amount of 2 times, right? So clearly the volume increases from 2 to 3, and in the same time the pressure decreases. So we can write that P2 over P3 is equal to N, which is equal to 2. Or if you want, you can write it in the opposite way. So P3 over P2 is 1 over N, which is equal to a half. So in part B, we have to obtain a relationship that links temperature, which is what the efficiency is based on, to pressure, because it's pressure that we know something about. And to do that, we're going to use the isentropic relationship between pressure and temperature. So I'm not going to derive that, but you can do that as an exercise. I'm just going to write the whole thing straight away. So from 2 to 3, so that is an isentropic expansion. So during the isentropic expansion, we have that P3 over P2 is equal to T3 over T2 to the power gamma over gamma minus 1. But remember, we're actually trying to find T3 over T2, so we should kind of extract this ratio from here. And to do that, we're gonna raise everything to the power gamma minus 1 over gamma. So T3 over T2 is going to be equal to P3 over P2 to the power gamma minus 1 over gamma. And that should be it. So T3 over T2 equals, so P3 over P2, we said earlier it's 1 over n. 1 over n to the power gamma minus 1 over gamma. So gamma minus 1 over gamma, and we can put the numbers in. So this is again 1/2 to the power 0.4 over 1.4. So the difference between part A and part B is that in part A, we have this, numerically speaking, we have 1/2 to the power 0.4, but in part B we have also 1/2, but there's a different power. Okay, so this is going to be 0.5 to the power 0.4 over 1.4, so that's 0.286 roughly. So let's see what this is approximately. So to the power 286, that is about 0.82. So the efficiency, which is 1 minus T3 over T2, is going to be 1 minus 0.82, which is 0.18, or about 18%. So compare that to the efficiency from part A, which was about 24%. So it turns out that, again, if you have an option to either expand the gas by by a factor of 2, or if you can choose to instead decrease the pressure by a factor of 2, it's the first option, that gives you a better efficiency? And that's the end of the question.